What's going on, guys? Stefan here from App Stuff, and before we dive into this awesome video covering interview questions on concurrency and threading, I wanted to let you guys know that this was taken directly from our iOS interview mastery course. If you guys want access to the full course to get a deep dive into interview prep for iOS, including system design, data structures and algorithms, and more, make sure you go ahead and check out the website and get access to this full course. The link for this is in the description. And I hope you guys enjoy. Now let's get back to the video. In this video, we're going to be covering interview questions on concurrency and threading and just overall general topics associated with these things. So this matters in interviews because concurrency is a high priority topic in iOS development and interviews because writing efficient thread-safe code is a real-world challenge in app development. And companies want engineers who can not only use concurrency tools, but explain the trade-offs between different approaches. So let's go ahead and dive in. First up, guys, what is concurrency and how does it work in iOS? So we're starting super general, super simple. Go ahead and pause the video and see if you can explain what concurrency is and how it works in iOS. A lot of engineers that I've seen can't give a straightforward answer to this question, so see if you can. Okay, so it's pretty simple. Concurrency allows multiple tasks to run at the same time, improving performance and responsiveness. In iOS, concurrency is achieved by using a few different things. One, we have Swift concurrency, which is the modern structured concurrency model that was released in Swift 5, I believe, and that uses things like async await, tasks, task groups, async let, so on and so forth. But there are other means of achieving concurrency in Swift. We have the Grand Central Dispatch, which was used before the modern structured concurrency model came out. So this manages queues for task execution. And then we have the operation queue as well. So this is the latter two options are sort of manual concurrency systems where we as the developer have to manage thread and task execution ourselves. Whereas the Swift concurrency model is the more modern structured approach where the system handles that a lot or under the hood for you. So that's a quick breakdown of what concurrency is and how it works in iOS. Next up, guys, we have another pretty general question with how does concurrency affect application performance? So I want you to think about this one and think about, one, does concurrency make application performance better or worse? And if it makes it better, how and why does it make it better? If it makes it worse, how and why does it make it worse? So on and so forth. So let's go ahead and dive into this now. So one of the biggest benefits we get with concurrency is improved responsiveness. So we get a smoother UI and an overall better user experience. So here is where you could start to show off some of your knowledge of threading, right? So we notice that with concurrency, we can keep the main thread free for UI updates, preventing lag and freezing. So if your application, for example, has some large scrollable list of data, you want the scrolling in that to be smooth. You want transitions between screens to be smooth. So the UI is obviously updated on the main thread, and we want to keep the main thread as free as possible and offload other tasks like intensive tasks, for example, networking, database queries, image processing to background threads. And concurrency allows us to achieve that. We can run tasks concurrently in the background while the UI is updated and maintained on the main thread. So that's a huge performance benefit we get from Swift concurrency. Next up, we have better CPU utilization. So overall, guys, modern iPhones have multiple core processors, and concurrency allows apps to take advantage of multiple CPU cores by running multiple tasks in parallel. So this is another massive performance benefit we get with the use of concurrency. We're taking advantage of the capabilities of our system, which in this case is an iPhone. So we can run multiple tasks at the same time, and this will ultimately lead to better application performance. You could imagine if we had a single threaded device or application where we had to have synchronous execution of tasks, where let's say we had 3 tasks that needed to execute. Imagine if task 1 had to complete before task 2 started and then before task 3 started, or imagine if we could run all of those in parallel and just get the data back as quickly as possible. That's what concurrency allows us to achieve. And obviously that just leads to faster execution and better performance, especially in computationally intensive tasks. And next up, guys, we are going to take a look at what is the difference between concurrency and parallelism. So these are two topics that are often confused with each other, and I like asking this question in interviews to see if the candidate really knows his stuff with the nuances behind concurrency. So concurrency, multiple tasks start and progress independently, but not necessarily at the same time. So that is the key component to understanding this. Concurrently does not necessarily mean the tasks are running at the same time. Those tasks can start and stop independently of one another, but that doesn't mean they're executing at the same time. So that brings me to my next point. Parallelism is when multiple tasks execute simultaneously on different CPU cores or threads. So that's the difference between concurrency and parallelism, guys, and that's a common interview question that you'll see come up. All right, next up, let's take a look. What is Grand Central Dispatch? So a lot of you may or may not have worked with this. If you've been doing or writing Swift for a while now, you've probably used the GCD or Grand Central Dispatch. But if you're new to Swift, this might be like looked at as some sort of legacy component that you might not know much about. So let's go ahead and take a look at what this is. So this is a low-level API for managing concurrent tasks and queues. So before Swift concurrency came out with stuff like async await and tasks and task groups and all that stuff, this is what we had to use back in the day to manage concurrency and the concurrent execution of tasks and offloading tasks from the main thread to the background thread and back from the background thread back to the main thread, so on and so forth. So this uses dispatch queues instead of manually managing threads. This supports synchronous and asynchronous execution, as does Swift concurrency. And it provides different quality of service levels. So here's what we see with the GCD queue types. So we have the main queue, which runs tasks on the main thread, like UI updates. And to access that, we say dispatch queue.main.something else. And then we have the global queue, which we can use for background tasks and different priorities, dispatch queue.global. And we can say run that on the background. That's that quality of service there. And then we have custom queues that are user defined, where users can manually define how they want tasks to be executed. So that's what GCD is, guys. Like I said, just a low-level API for managing concurrent tasks and using queues. And you will often be asked about that in interviews. Okay, next up, this one's interesting. What are synchronous versus asynchronous tasks in GCD? So this is going to test your knowledge of a couple things. Do you understand what a synchronous versus an asynchronous task execution is? And do you understand that within the context of GCD and also other things like Swift concurrency and stuff? So we notice that synchronous tasks block the current thread until the task is completed and the next task can start. So things have to happen in order, right? So this is obviously slower for application performance, but does have its time and place. So try to think of some examples with when you would want to use a synchronous execution of tasks, guys. So one that I can think of off the top of my head is if you have chained network calls or you're fetching data from an API that involves some sort of chaining where you have to do one task and then another to fetch data in sets. Well, you might want a synchronous execution of tasks in this scenario because if you have data call 1 and then data call 2 is dependent on information that comes back from the first data call, then you need to run those tasks synchronously, right? Because fetch 2 or the second fetch needs information from fetch 1 to get that information or get you what you need. So that's an example of when you could use a synchronous task execution. Async tasks are the opposite. So they run in the background without blocking the current thread, and multiple tasks can execute at the same time or run in parallel. And you don't have to wait for one to finish before the other can start. So here's a nice little challenge that I like to give people in interviews. I have received stuff like this myself as well. The answer is obviously at the bottom, but see if you guys can figure out why. So we create some queue and we want to run some tasks synchronously, then asynchronously, and then just in the regular execution of the program outside of the queue. So see if you can figure out why those tasks come back in that order. As you can see in the output, we get task 1, then task 3, then task 2. So guys, the reason for this is because the first print statement is what's known as a synchronous task. So that has to complete before the program can continue execution. We see that the sync task blocks the current thread until that task is completed and the next task can start. However, the next one is asynchronous. So this will not block the current thread and program can continue execution while the async task runs. So we get the next print statement as task 3 because the program continues with its execution and is running that asynchronous task on the background. And then after that, we print statement of task 3, it comes back and gives us the print statement of task 2. So that's a really, really simple example that tests your knowledge and understanding of how synchronous versus asynchronous tasks work in running on a particular thread of execution. I don't like to get more complex than that. Some people get way too complex with these things, and it's like, I understand that, the utility behind that, but I like to keep it simple. But you can get pretty fancy with these examples and have a bunch of nested tasks within one another. And there's plenty of examples you guys could find online if you really want to test your knowledge of this stuff. But that's good enough for me, so let's keep going. Okay, what are the differences between async await, or the new modern structured Swift concurrency model, and GCD? So this is a common interview question that you'll get because right now a lot of companies are in the process of writing most of their new code using async await and probably converting old code that uses Grand Central Dispatch to async await. So understanding the differences between the two and also knowing how to rewrite one and refactor it into the other is very important. And that is, at least right as of now in 2025, an ongoing thing that is happening in the iOS community. So guys, to answer this question, async await provides a structured concurrency model. It has built-in error handling as well with do try and catch, and it reads like synchronous inline code and is easier to debug. So overall, I guess what this question is asking is not just what the differences between the two are, but what are the benefits of one versus the other. And obviously, the async await model has significant benefits over using GCD. GCD, on the other hand, requires manual thread management. Error handling is more difficult. It requires you to use completion handlers, which is really messy and prone to retain cycles, and it's overall harder to debug. So if you guys have ever used completion handlers, they're pretty nasty, and they are just significantly more error prone because of reference cycles that we saw in our section where we talked about closures with retained cycles and with memory management. You have to use nasty keywords like escaping. Error handling is not implicit, or it's not like easy to do. It requires a lot more custom error handling. There is the result API type or result type you can use with your completion handlers, but overall, the Swift concurrency model makes error handling significantly easier with do, try, and catch, or throwing functions, right? So those are some of the major differences between the two guys and why one is better versus the other. If you've ever had to use nested completion blocks, it's an absolute mess. So now we're getting into some more of the fun stuff. So what are race conditions and how do we prevent them? So go ahead and pause the video and see if you can explain what a race condition is and how we can prevent race conditions from happening. So a race condition occurs when multiple threads access and modify shared data at the same time, leading to unpredictable behavior. So we've sort of touched on this concept when we talked about the differences between classes and structs. And race conditions can happen with classes because we have multiple threads that could potentially modify some shared data at the same time, leading to unpredictable behavior. I've had applications crash because of this. You have applications that don't reflect the correct state that it should be in with race conditions, guys. So here's how we can prevent them. We can use actors, NS locks, or synchronous task executions with dispatch queues. So you don't have to worry with race conditions when your task execution is synchronous because only one task is happening at a time and only one task can modify your data before the next one begins and potentially modifies that same piece of data. You can also use NS lock. This is something that I was recently made aware of. I think it's definitely older, but you can lock threads during the modification or process of that thread ongoing and modifying data, and then you can unlock the thread when the next task begins, just to ensure that threads do not have concurrent access to the same piece of data. And the more modern approach is using actors in Swift, and we are going to get more into actors in this section as we go. So next question, as a follow-up from the last one, what are actors in Swift concurrency? So go ahead and pause the video and see if you guys can break that down. So actors in Swift prevent data races by ensuring that only one task accesses a property at a time. So this is part of the more modern structured Swift concurrency model, guys. And actors are essentially a reference type that prevents data races. And as we can see, it prevents race conditions in a multi-threaded environment. It serializes access to shared data. So when utilizing actors, you have to utilize the await keyword when working with that actor, and properties and methods associated with that actor as well. So because we have to await for something to happen, it sort of creates this synchronous or serialized access to shared data, guys. So that's that. Next up, what is async let and how does it differ from await? So async let, let's go ahead and dive in, allows multiple asynchronous calls to run concurrently instead of sequentially. So even though, like when using the await keyword, that essentially creates a suspension point in your code, and your code can't go any further until that process completes. When you say, hey, wait for this to complete, then I can continue. So you do get sort of this synchronous or inline behavior with your code when using async await. Well, async let allows you to circumvent that by allowing multiple asynchronous calls to run concurrently instead of sequentially. So it's a really cool feature. Unlike await, which waits immediately for a task to complete, async let starts the task and execution of the program continues until you actually need to use the result. So you can say, hey, async let this, async let thing 2, async let thing 3, and let the program keep running until I actually need to use that data at some point. Whereas with async await, if you did thing 1, thing 2, and thing 3, if you said await thing 1, await thing 2, await thing 3, they would come back in that sequential order and sort of behave in that synchronous context. Key benefits: using async let reduces overall execution time by running multiple async tasks in parallel. So this is something that I use quite often in my code and something that you guys should get some practice with. We have a full course on Swift concurrency that I will show you guys at the end of this if you want more practice with Swift concurrency, guys. What are task groups and when should you use them? So this is another big feature in Swift concurrency. Task groups allow you to dynamically create multiple concurrent child tasks while managing them as a group. So this is also something I use very often, and it overall reduces the amount of runtime necessary to complete a group of tasks. Key benefits: dynamically spawn multiple tasks inside the group, so you can create multiple tasks at the same time within a task group, and they will execute asynchronously. Automatically waits for all tasks to finish before returning the results. So although we are creating this like sort of group of tasks, all of the tasks have to finish before we can actually use the information. So this actually helps give us more defined structured behavior when using the task group. So it's really helpful. We have more flexibility than async let because we can add tasks dynamically. And to wrap this section up, guys, we have a more basic question. How do we ensure UI updates happen on the main thread in Swift concurrency and Grand Central Dispatch? So pause the video and see if you guys can think of the different techniques that we use to ensure that UI updates happen on the main thread. So imagine that you offload something to a background thread like a network call or some video or image processing. How do you ensure that that update happens on the main thread on the UI? So we have a couple different options. We can use main actor.run. We can use the main actor macro in Swift UI, and in GCD we have dispatch_queue.main.async or dispatch_queue.main.sync, and those will transition our updates from whatever background thread the execution was happening on back over to the main thread. So that's going to wrap it up for the concurrency section, guys. We covered a lot of different topics here, and I think that these are the main things that you're going to see in interviews when talking about concurrency and threading. And if you guys want more practice with this stuff, we have a full course on mastering Swift concurrency on the website at stephancodes.com. The link to that will be in the description to this video or listed somewhere. But if you guys want to find it yourself, you can go to stephancodes.com and go to the courses section, scroll down to fundamentals, and you will see mastering Swift concurrency there. So that's a much deeper dive into all of those concurrency examples. And we build real life applications using modern Swift concurrency. And that's going to wrap it up for this video, guys. Hope you enjoyed. We'll see you in the next one. Peace.